welcome to all, and thank you for putting the time aside to attend this webinar. I'm going to quickly run through a couple of slides just to introduce the Concrete Society and just show you guys some of our core values and give you a bit more feedback and background to what the society does, how we're involved in the industry and so forth. And then I'm going to hand over to John. So in a nutshell, our 6 core values is modern and advanced, relevant, streamlined and efficient, objective, inclusive, and loyal. Our committees that we have is the inner branch with Michelle, KwaZulu-Natal, we have a branch, Donovan, Western Cape, and then Prof. Billy, the RMC committee, the FIP committee, head of delegation there is Sarah, and then the cement branch committee by Mark. We are currently busy with a membership drive since the Concrete Society has only recently started up again after closing down in 2024. And we have a special running in a sense of half-year fee rates. So please, if anybody is interested, you're more than welcome to have a look on our website. These individual membership packages as well as the company memberships are listed there. And as I said, if you join now, you will qualify for half-year fee rate. Some of our current members, just to give you background, Chrysler, Quick Group, on the Emerald members, Koolstraat, Mapai, Meteor. You will note these are all well-known players and suppliers and contractors in the concrete industry, as well as consultants. Just running around through all of our different memberships. Obviously, the Concrete Fix is in its season number 5. Today, it's Concrete Fix 510. Obviously, keep these future dates in mind. The ones coming up on the 23rd of October, presented by myself through Infinite and Koolstraat. Then Yaku from Afrimat on 20 November, and then Vandi Olivier from ACOM on the 19th of Feb. And then we also have the concrete classes coming up on 6 November and 5 Feb. Branch activities, events to keep in mind, site visits, quarterly technical talks, careers in concrete events, networking events. It's all obviously at our branch activities that you need to keep in mind. I'm more than welcome to participate in. CPD points, especially for the consultants. Extra CPD points are available to Concrete Society members, which are some of the benefits. And by attending these Concrete Fix events, you do qualify. And Natasha will forward an email to all delegates when the CPD points have been finalized and locked on our website. And a recording and copy of this presentation is always available. You can, or if not on the website, request it through Natasha. And the allocated CPD registration number works as follows. Listed there at the bottom. I think that's quite clear. Obviously, if you have any problems, you're more than welcome to contact Natasha at CSSA. And then basically, please feel free to visit us on our website, concretesociety.sa.org.za. And then in closing, the success of the society relies on the commitment and support of individuals, companies, and stakeholders from cement and concrete industry. Thank you for your ongoing contribution. Then without further ado, I just want to introduce our speaker today, Back to Basics, this concrete class. 1.8, the fundamentals of concrete technology for concrete practitioner. The presenters, John, who has a BSc in building science, who has a BSc building science degree and is a member of the Institute of Concrete Technology in London. In 2009, he joined the Cement and Concrete Institute as a lecturer in the School of Concrete Technology. remained in this role until the demise of the Cement and Concrete SA in 2024. While employed at the Cement and Concrete SA, he ran the Advanced Concrete Technology Diploma Program. That in short is background to John. John, I would like to welcome you to this concrete class, and we all appreciate you putting the time aside to do the class. And I would like to hand over to you.
Thank you very much, Willie. All right, so I'll go ahead and try and share the screen. All right, it's come up on my side that I'm just seeing the screen. Are you guys seeing the screen?
Everything is fine, John. Thank you.
Okay, great. So we can start. So thanks very much for having me, and welcome to everybody. I must admit I'm quite pleased with the numbers that attend these classes. This presentation, let's see if I can just forward it a little bit. It's not forwarding, just hang on. Let me just start this again. We practiced this earlier. Sorry, guys, I just can't get my I just can't get it to forward. Oh, there we go. Okay, cool. All right, so I just want to start by saying this is a very low-level presentation on concrete rheology. At the end of this, the few slides that I've put together, I just want you to have a feel. I want you to start thinking of concrete in terms of concrete rheology, and consider, I want you to start linking the tests that we do on fresh concrete with the rheological parameters in concrete rheology. I've based this presentation on a chapter in this book called Advanced Concrete Technology. It's a chapter written by Dr. Peter Damone, and it gives a lovely sort of walkthrough of our consideration of concrete rheology, considering the tests, what we call the single point tests that we do on concrete, and then a quick and brief description of concrete and its the concrete rheology curve, and then we'll talk a little bit about the machinery or the apparatuses that measure the concrete rheology. Let's hope this works now. All right, cool. All right. So just an introduction. A concrete practitioner needs to specify the fresh properties of concrete. He has to have some sort of way of saying how he wants that fresh concrete to turn out. And usually he does that by specifying a value of a test, for example, a slump or a VB time or from the flow table. Once the mix is done, there must be some sort of way of measuring that the right fresh properties are obtained. And these are, I think you all are familiar with that. The slump test, flow table tests, and the other tests that are available. And if the concrete fresh properties are not to spec, then the concrete practitioner will need to know how to adjust the mix to bring it back into line with the original specification. And we're quite good at this. We do a slump test, and if the slump's not high enough, what we do is we add a bit of water, or sometimes we add a little bit of plasticizer. So we get quite good at adjusting the mix. But I'm not sure if we're always doing the right thing. And it's not always easy when you're using common tests we use on fresh concrete to actually make the right adjustments to the mix when it's not right. Sorry, guys, I'm having endless problems with this. Okay, I'll just use the enter key to get it to go forward. So some of the basic requirements of fresh concrete, we must be able to place and compact it easily. So concrete, normal conventional concrete, we don't want to flow. It's a thing we really want to avoid. You know, using a poker vibrator to flow the concrete is a no-no. You get segregation. So we wanted to just be able to flow a little bit around the reinforcement into the corners of the shutters, and it hold together while it's doing that. It must remain homogeneous with little segregation. And included in that segregation, it mustn't bleed too much. In some cases, we do want it to bleed a little bit. In cases of, for example, industrial floor, you want it to bleed a little bit. So when we're placing or transporting and compacting it, we don't want that mix to fall apart. So we've got to design that into the fresh properties of concrete. And then, of course, we want a good off-shutter finish, and we must be able to work the surface, for example, in industrial floors, work the surface easily and get the right finish on the floor. And then this is when, the contractors have a heart attack, because the concrete is mixed, and then we've got a very, very short time to get that concrete transported, placed and compacted and finished off. Its properties, its fresh properties are constantly changing from the time it's mixed. People don't understand that it's the second you add water to your concrete mix, the second the water touches the cement, it actually starts hydrating. And then the rheological properties of that concrete, the fresh properties of concrete, start changing because of that. It starts very slowly in the beginning, but it is actually hydrating. And then that second point, it's very important to understand that what happens in the fresh state, what we do to the concrete in the fresh state, is very closely linked to how well the concrete's going to turn out, how strong it's going to be, how durable it's going to be, and how well it's finished. So it's a very important part of concrete technology, is the fresh state of concrete. All right, so there was this guy, Professor G.H. Tattersall. He's sort of renowned as the pioneer in concrete rheology. And he wrote a very good book that used to be in the Institute's library, called Workability and Quality Control of Concrete. And he was also instrumental in designing what I'll describe later as the Tattersall two-point testing apparatus. So he proposed 3 different workability classes. Class 1, qualitative, and that's just a class where we just describe the mix using words. And then class 2, a quantitative empirical class, and that's the test that we do on fresh concrete, the common test that we do on fresh concrete, where we give it a experimental value. We do a test and we get a value for it. For example, slump, we get millimeters, VB time, we get seconds. And then the third class is quantitative fundamental, which is basically then describing the concrete in terms of rheology, in the terms of the standard definitions that you would find in national standards for rheology. Right, so the class 1 quantitative is basically the eyeball method. So the person observing the mix decides if it's suitable using his eyeballs and his brains. The eyeball mix design is often used in the mix design process. And in fact, my experience is a lot of the laboratories around the country, They don't do any fancy mixed design process. They use what we call an eyeball mixed design process. Through experience, they put the constituents together. They roughly know how much of each material needs to be put in. And then they use their eyes and brains to decide if it's workable enough, if it's flowable enough, etc. But no measurable values are given to the fresh properties. So let's say you've mixed your concrete at the ready mix plant, and the guy looks at it and he says, "Yeah, no, that's great. It's got the right workability." When it arrives on site, there's a second observer. That observer has to have the same meeting of minds as the guy at the ready mix plant, and rarely will you get that. So there's a problem with that. There's no measurable way of saying if it's right or not. Whereas with the class 2 quantitative empirical description, simple tests are done on the fresh concrete and they yield a single quantitative empirical value. And so we refer to these as single point tests. All right, so you'll see that you get one value coming out of these tests. And they're about, I think I last counted, I think the one time I did look up, and there were about 33 different tests you can do on fresh concrete to give an indication of the workability. So what we'll do is we'll go through a few of them, and we'll have a look at them and see what they're sort of measuring. Right, so there's a list of some of the tests. So I'll go through some of the more common ones, and we can see what they do. Right, so the one that we all know is the slump test. And in that diagram, it gives a lovely convex shape of the slump. That looks like a true slump. And that's what a slump should look like when you do a slump test. Unfortunately, when we do slump tests, we see that often half the concrete is sheared away or there's a total collapse. And we still measure the slump, which is not really the right thing to do. The slump test is a wonderful thing. It's not going to measure workability, but it gives you an idea. And it's universally used, very simple equipment to carry around. And most of our concrete is specified to have a certain slump. So when it arrives on site, they can do a slump test and they can send back the concrete if it's not correct. Some of the problems with the slump test is very, very low precision of results. In other words, it's both inaccurate, but also repeating the test gives you very different results all the time. So, and it's very operator sensitive as well. We've learned how to work with it, but it's not the most accurate and precise way of measuring. I've drawn a red line through, just an arbitrary red line through that slumped concrete. And that's, I want you to imagine as represents a plane, a horizontal plane cutting that slump test, that slump. And what's really happening, you know, in rheology, we're going to be talking about the yield stress and the plastic viscosity. So what's really happening is the concrete slumps down. And as it slumps down, that cross-sectional plane gets bigger and bigger. So the stress gets lower and lower. It gets lower and lower until a point where the concrete can hold its position and stop flowing. And so you will see later that slump is really giving a measure of the concrete's what we call yield stress. So you'll link that later when we talk about the actual rheology of concrete. All right, so here it's from the sands. It might have changed. I just found this. It might have changed, but just looking at the tolerances allowed in the sands document for ready-mix concrete, you can see that there's a wide range. You know, for example, for the 50 to 100 millimeter slump, you've got plus minus 25. For over 100 millimeter slump, you've got plus minus 40 millimeters you're allowed. So it's not so, how can I say, it's not so precise. And you'll see that with measuring more accurately with a rheometer, you'll get a much more precise way of looking at concrete. Here's the VB time. And there basically what happens is you do a slump test within a cylinder. I think most of you know this anyway. And then there's a vibration table and you vibrate that concrete down. You put this disc on top of the concrete and you vibrate it down until it's horizontal. So it measures very low slump or no slump. It gives a measure for no slump or very low slump concrete. The equipment is not so big, so it's ideal for a site lab. It only can be used for very low or no slump mixes. One of the problems is that you need a stopwatch and you need somebody to time. So from the time the vibration table goes on to the time it levels out in that cylinder, he takes the time. So I think there's quite a bit of inaccuracy built into that. I mean, if I was doing it, my reaction times probably is not as quick as a youngster. And so you get a bit of inaccuracies there. All right, the flow table test. This, I think we should be used more often. I've never once seen it used on site. Hopefully people are using it. I remember there was I don't really want to tell you the site it was on, but the Italian contractor on the site insisted on having a concrete with a slump of 200 millimeters. Now, that is to do a slump test with a concrete with 200 millimeter slump. It's the wrong test. And they should have been using this flow table test. It would have given a much better, more accurate reading. There are certain problems, you know, the slump is the cone is a little bit shorter, and you do basically a slump test in that cone, and then you use this handle to lift it up to a point where a stop there, and you drop it 15 times. Now, if the operator lifts this handle up vigorously and bangs into this stop here, you're going to skew the results. So there are certain problems. It is operator sensitive, but for high slump concretes, it's probably the better system to use, and you need to put it on a very level surface to use. So that's another. And they're basically, once the concrete is slumped down, you measure the diameter of the slumped concrete in two directions to get a reading in millimeters. All right, let's go to the next one. Compaction factor. There was one lying around in the lab. Never ever seen this thing used, but it gives an idea of how easily the concrete compacts. And basically, you put the sample in the top cone. There's a trapdoor that lets it fall to the next cone, and then you open that trapdoor, and it falls into the cylinder. And then you need a scale, because you measure the mass of the semi-compacted concrete in the cylinder, and then you fill that cylinder up and fully compact it. And the ratio of the semi-compacted to the fully compacted mass of the cylinder is the compaction factor. Not easy, never seen it used, and but it does give this height gives a sort of good measurement of work. It allows you to apply a set amount of work to the actual concrete. Then you get all the self-compacting concrete tests. If you ever want to look up and find out about self-compacting concrete, there's an excellent publication put out by FNOC, called the European Guidelines for Self-Compacting Concrete. You can Google it and download it. It's one of the best publications. It gives you all the different tests that you can do on self-compacting concrete. And you'll notice that with these tests now, because self-compacting concrete flows easily, they deal more with, instead of the what we call the yield stress, they deal more with the plastic viscosity of the concrete, especially this V-funnel test. You measure the time it takes for the concrete to flow out of this, and it gives you a much better idea of the actual viscosity of the concrete. Right, so the question is, are single point tests giving you the full picture? So I'm going to put up a couple of slides to just show you that you can't really, between the different tests, you can't correlate easily. So here we've taken on various concretes, we've taken the VB time and the slump. Now you would expect that these fresh concrete tests would have some sort of correlation. You get a straighter line, but you don't. So if you look at that first graph, you can see that for lower slumps, you get a wide range of VB times. And then for the mid-range slumps or the highest slumps, you get very similar VB times. And then on this one here, we use the comparing the compaction factor to the slump. And you can see at very low slumps, you get very different compaction factors, whereas at higher slumps, you get similar compaction factors. So there's no clean correlation between the different tests. So this also shows they took 4 mixes and they did these 3 different tests, slump, VB, and compaction factor tests on them, and then they ranked the concretes in order of their workability, going from left to right. And you can see you get very mixed results, very mixed results. Having said this, if you look at the slumps, they're very similar, and if you look at the VB times, they're very similar. So I'm not. It doesn't really convince me too much, this, but it is trying to prove the point that you can't correlate the different tests. Right. So because of that, considering the limitations of Class 2 single point workability tests, the common tests we do, these are the common tests that we do on the concrete. There's a strong argument to move to the Tattersalls proposed Class 3 workability testing, where testing is done in terms of the concrete rheology. Okay, so there's a strong argument, but it's not that easy because of the machinery required. But I'm hoping somebody here is watching and maybe consider taking this up and maybe doing a little bit more research on this, because there is potential for this to be used effectively, both in ready mix plants, pre-cast aspirations, and even on site. Right, so I did a Google AI definition of rheology, and really, so it's from AI, so it must be correct. But anyway, I just put in bold the points that I just want to read out. Rheology is the science that studies the flow and deformation of materials, examining how substances respond to applied forces or stresses. And then by understanding these properties, the scientists and engineers can optimize material processing, ensure product quality, and develop innovative materials across various industries. All right, so I'll bring that up in a slide later, but there is potential to make good use of concrete rheology. Right, so a very low-level definition, how we describe in rheological terms a matter that's flowing. So if you can consider a section of a flowable matter, such as water, it's defined like this. If you've got a force across a cross-sectional area, consider that sort of divided into different plates. So a force across a cross-sectional area giving what we call a shear stress, and that will cause a deformation, which is the X, and we define the shear strain is that X over the base height over which that deformation has occurred. And then if we take the derivative of that against time, we get that gamma dot, which is the rate of change of shear strain. So we can draw a curve of a material using what we call the shear stress, which is the load over the area, the cross-sectional area, and against the rate of change of shear strain. So by plotting the shear stress against the rate of shear strain, a flow curve can be drawn. A simple form of flow curve can be demonstrated by plotting a flow curve for water. All right, so guys, when I drew this, I didn't, you'll see, I didn't quite get this angle right. It should be closer to 45 degrees for water. But anyway, if we plot it for water, we find that the line, the graph goes through the origin. And then the slope of that graph is what we call the coefficient of viscosity. And we call that type of flow linear Newtonian flow. And you'll see later that concrete's not quite like that. It's what we call a Bingham material, but I'll describe what that is later. All right, so the units are given in, so the units of the viscosity are given in, well, I think the next slide actually gives, no, it doesn't. Okay, given in Pascal seconds. I just wanted to put this up, you know, this is the Queensland pitch drop experiment. Some of you guys might have seen it. It's the longest running lab experiment in the world. It was started, they started preparing the experiment in 1927. They actually started in 1930. And they've got a flask of pitch. And that pitch automatically flows. It's got it flows. It's very close. Well, they can't really check whether it's close to Newtonian flow or not, but it does flow. And typically, it used to drop 1 drop of pitch every 9 years. It's dropped 9 drops altogether. And they changed in 1988. They put air conditioning in the lab, and basically what happens now, it drops every 13 to 14 years. Nobody has actually seen that pitch drop. But I just wanted to show you a very, very highly viscous material. It's almost, I think it's almost 33, we'll see on the next slide, 35 billion times, or 35 billion times higher viscosity than water. So I just thought I'd put that in for interest. So the viscosity units are measured in millipascal seconds, or Pascal seconds. So water has a very a viscosity of close to 1 millipascal second. And you might see this, might see it written as centipoise. All right. So there's some examples of the viscosities of different materials. And you can see water is quite close to 1. And there's honey. So I think concrete would have a viscosity typically from honey upwards. Right, so there you can see pitch, according to the website, of the Queensland website, 230 billion times higher viscosity than water. All right. Some materials, such as a concrete, will only start flowing after an applied shear stress reaches a threshold value. Now, you saw with the slump test, it slumps down to a point where that cross-sectional area gets big enough, and then it stops flowing. It has to overcome, the stress has to overcome a certain threshold value to start flowing. And this value we know as yield stress. So a material that has yield stress with a linear flow curve is described as having Bingham behavior. That's the way we describe it. And the Bingham module is sufficient for most concrete types. All right, so there's an example of a flow curve for concrete. And that tau 0 is the yield stress. And it, for most purposes, it's a straight line. Some materials you get what we call shear thinning. So basically the curve goes up steeply and then thins out. And shear thickening, it starts off shallow and then it steepens up. That's called shear thickening. But for most purposes, we can consider concrete like this. So most concretes require to overcome a yield stress before it will start flowing. And one of the ways we can overcome yield stress is using a poker vibration. Right. And then, of course, the slope of the grass is what we call the plastic viscosity. And you can see the equation is basically a straight line equation. Mu being the plastic viscosity. So here are different flow curves for different types of concrete. It's sort of imaginary, I just made it up, but you can see for the red line here, conventional normal concrete, sprayed concrete, like shotcrete, this green line here. Can you see you want to be able to spray it onto a wall, and then you don't want it to flow off the wall. So it must have a high yield stress. They do that with some kinds of paint. You know, you take a paint and you apply a stress to it, and it becomes liquid, and you can paint it on the wall. But then it's got a very high yield stress, so it doesn't flow off the wall. Look at the self-compacting concrete. Often it's got self-compacting concrete has got quite a high viscosity. That's the slope of the curve there. But the plasticizers and super plasticizers drop the yield stress right down so that they flow immediately. They might flow slowly, but they flow easily. Ultra high performance concrete, the blue, often because of the high amount of binder in it, has quite a high viscosity, the slope of the graph. All right, so here is an example of where we compare the yield stress to the plastic viscosity. And this is where knowing the 2 points, the 2-point testing of concrete, in other words, the yield stress and the plastic viscosity, gives us a much better insight into what's happening with that concrete. So we know that, for example, more water will increase less water will increase the yield stress and the plastic viscosity, whereas more water will reduce both of those. Water being the major lubricant in concrete. And you can see what happens with fly ash and slag. I just want to point out this red line, the less paste and more paste. In the next slide, you'll see that there's contradiction. So one of these slides is incorrect. I'm not sure which one is, but they're both produced by very good researchers. So I'm not sure which one is correct, but anyway, you can think it through later. But I just want to give you one scenario. For example, at a ready mix plant, they mix the mix, and then they find that the slump is too high. Now, what the initial knee-jerk reaction is, they might say, there's too much water in the mix. But they might be incorrect. It might be too much plasticizer or super plasticizer in the mix. And by being able to do a test on the concrete to see its actual 2-point rheological parameters, you'll be able to see whether it's the super plasticizer causing, or the plasticizer causing the problem, or the water causing the problem. Because once you do it, you can see if the yield stress is just dropping, but the actual plastic viscosity is staying the same. In other words, the slump is bigger because of the drop in the yield stress. Then you know that you've overdosed it with plasticizer. But if the plastic viscosity was dropping along with the yield stress, then you know you've got too much water in the mix. So this is a much more accurate way of deciding what has gone wrong with your mix. You can do this likewise with aggregates. Here's a nice cubic-shaped angular crushed stone. And if you increase the flakiness or elongation of the stone and the rougher surface, you'll find that the yield stress goes up and the plastic viscosity goes up. Can you see there's contradiction? Here it says more sand. The previous slide it said less paste. So there's a contradiction there. I cannot describe what went wrong there. But anyway, this I got from a slide from Dr. Wolfram Schmidt, very respected concrete technology researcher. So you could use rheology also to see if your aggregate is changing shape. It would be able to point to you whether your aggregate is changing shape, and you could correct it accordingly. All right, let's talk a little bit about the machines that we can use to measure rheology properties, the requirements. The problem with concrete, it's got stone in it, and that causes all sorts of hassle because the stone is quite a harsh material. And so you've got to design a machine that can actually, or apparatus that can handle enough of the concrete, typically more than 10 meters, and must be able to handle a wide range of concrete types, and strong enough that it doesn't wear down and break with the stone. So there are three main test systems that have been developed. I'm not going to describe these two, the VML viscometer, which is basically a solid cylinder within outer cylinder, and the concrete fills the outer cylinder, and they basically turn relative to each other. The BT rheometer, which is basically you put the concrete between two rotating horizontal discs, and then this apparatus, which they often call the two-point workability tester, pioneered by Professor Tattersall in the 1970s. So we'll talk a little bit about that. And this is where I'm hoping that I've got somebody's out there that maybe wants to do a bit of research on this. There's a machine, there's a Tattersall Mark II machine sitting at UJ. Some of you might have gone to UJ, so you might know this machine. Unfortunately, I've got beautiful pictures of that machine, but I was not allowed to publish them. So I just found this arbitrary looking machine, which looks quite different to the one at UJ. So please, can I ask if any of you know that machine, have got photographs of it, if you could send those photographs to Natasha, and then we can put those photos on in this photo. But that's what it looks like. It's quite a simple machine, and it's designed basically on a mixer. It's almost like it's a mixer. This H shape is more for low slump concrete, but the one I'm sort of more interested for high slump and conventional concretes is the one with the two impeller, or the impeller system. And that basically rotates within the concrete, and it can move freely within the concrete, so you don't get any shear planes built up. And so you can measure the rheological properties of the concrete with that. And the output of the device is shown in the equation T, which is the torque in the rotational speed, and then the terms G and H are related to yield stress and plastic viscosity. And then this last point here, the device can be calibrated in order to determine yield stress and plastic viscosity in fundamental units. This is great if you really want to know the actual plastic viscosity, but what I'm proposing here is that it would be great if somebody could take that simple machine and make a standard machine out of it, like a slump cone, where you just measure millimeters. If you make a simple machine that just measures pressure or torque or something like that, gives two values that you can relate to the actual yield stress and the plastic viscosity, that would be great, and you'd get some pretty nice results and control over your concrete by knowing that. So the advantage of this apparatus, it can test a wide range of concretes from very low slump to very high slumps. Two-point testing describes the concrete in rheological terms, and the option to change impeller design to suit concretes. You can always change the impeller setup to suit different concretes. And for example, a precast and ready-mix concrete operation could make very good use of these. Instead of doing the slump test, in fact, most precast and ready mix plants, they don't even do a slump test. They do an eyeball test. The guy looks down into the back of the truck or the mixer, and he decides for himself what the slump is. They get pretty accurate at that. You guys that work in these plants, they get pretty accurate at deciding what the slump is. But wouldn't it be nice to be able to take a sample and actually put it through one of these apparatuses to see that you've got the right rheological properties? Too often I see at precast yards where, especially with extruded concrete, something like that, they put the concrete and start trying to extrude it, and it doesn't work at all. It just flops down. At the moment, this apparatus is too bulky and heavy to use on site, but it is suitable for labs, site labs. The one thing I read up is that mixing for too long can segregate the mix. So there we go. Needs to be developed further and simplified. Right, so we're just going to end off. I've got 3 more slides. We'll just end off quickly. So I just want you to think about this. It's all very well having the lovely rheological properties of concrete down to a T and specifying them. But remember, from the time of mixing to final placement, the fresh concrete's rheological properties are constantly changing. So we have to always cater for that. And there are 3 things that make you lose workability. And I can tell you workability is the major cause of loss of durability and strength in concrete, because if you lose workability, you don't get the compaction that you want and the finishes you want. So the 3 things are loss of water, and that's due to evaporation, absorption into the aggregates, and the hydration of the cement, all made worse by low relative humidities and high temperatures. The hydration of the cement also speeded up by high temperature. And then, of course, admixtures lose their efficacy after a while. They get absorbed onto the surface of the cement, and so they only last for a certain amount of time. Then you lose the effect of that. So we've got to be aware of that with concrete in the fresh state. Also, we've got to remember that concrete is a thixotropic material. And a thixotropic material is like all-gold tomato sauce. If it's allowed to settle, concrete is allowed to settle for a certain amount of time, there's a certain amount of structural buildup, hydration of cement, and also a certain amount of natural compaction due to the bleed water and everything coming closer. So it tends to stiffen. So it's not actually showing its actual rheological properties. That stiffened material has to be worked again to get back to its rheological properties. So just remember that with concrete. It's very, very evident in self-compacting concrete. You make a batch of self-compacting concrete and you pour it into a wheelbarrow or something like that. You find after a short while it stiffens up, even though you still got the behind the scenes, it's got the same rheological properties that you require. You just need to mix it up again to get those. Right, so there we go. So there is a need to keep fresh concrete agitated to maintain desired properties. Right, so ending off, rheology as part of concrete technology is important for, and I got these from Dr. Wolfram Schmidt. Optimizing the use of constituents make up the concrete. So we can, we're always trying to use cement as efficiently as possible. And by doing this 2-point testing, we've got the potential to do that. And by having a closer control over the concrete, our safety and robustness increases. We meet the specs more often and we get the right strength. And linked to that also, we get the right durability and we get the right ease of handling and placement and compaction. And then linked to all of these 3 things above is sustainability. If you've got strong, dense, well-compacted concrete designed properly, it's going to be durable and more sustainable. And then, of course, concrete rheology can play a part in innovation. These fancy shapes, slender elements, and then, of course, 3D printing, the concrete ink. relies very heavily on concrete rheology. So that's just a general overview, and I think we can leave it at that, guys. Thank you. Right, that's it.
Oh, yes, thank you, John. Thank you for this very informative concrete class. I really enjoyed it. Thanks a lot. I think everyone definitely picked up and learned a bit more. I would like to open before we leave maybe the floor for a couple of questions. Anyone wants to ask something to John?
Okay.
Maybe you can just put your hand up if there's any questions. I don't see any, John, so I think
We can leave it.
congrats. Yeah, we can leave it at that.
Okay.
The
Well, I
class-
can I just again, look, I'm out of concrete now. I'm basically retired, but there is that machine sitting at UJ, and if there's any student on this on this session, please would you consider doing a project or a thesis or something with this, because I think there's a potential for using a simple machine that measures 2-point measurement of concrete. You're going to get much better results. All right, so that's my request.
100% noted. I think that will bring us to the end of this concrete class. And as I said, John, very thanks a lot for putting the time aside and giving and presenting this class to us. Thank you so much.
All right, no, that's a pleasure. Thanks, guys.
Okay, thank you everyone for attending.
Thanks.
John, can you just stay on the line?
Okay.
And Willie, if you're still here.